with Ravi Chugh, my advisor, Mitch Spranlin, Jacob Albers from the University of Chicago. I'd like to show you a first milestone in combining programmatic and direct manipulation. We've all used what you see is what you get applications where we manipulate the objects in the document directly. Graphic editors, presentation software, and word processors all allow the user to directly manipulate the objects the user wants to change. For most people, this direct manipulation is the normal and expected way that computers operate. If you want to change something, you click on it, you drag it, and you change it. Direct manipulation is intuitive and powerful. In some cases, however, direct manipulation can become overly repetitive. Copy-paste often helps, but it cannot always capture the actual relationships between the objects. Clearly, creating a design like this can become tedious. Moreover, if the user ever wants to modify the design, it might be just as hard as creating it in the first place. The design of the branches on this tree, they will have to either edit each branch or start over from scratch. As programmers, we might instead our graphic using our favorite general purpose programming language. But there are trade-offs. We lose the fluid workflow of direct manipulation. You know how it goes. You run the code and it doesn't look quite right, so you go back and change a number in your program, and then you run it again. Still not quite right. So it again and change another number in the program, and oh my goodness. Is there a better way? Instead, wouldn't it be great if, once you see that the output of your program isn't quite right, you could directly change the output, and then the system synthesizes a program update to match. This ideal workflow is what we call live synchronization. And live synchronization is a particular kind of program synthesis. We want to facilitate an interactive workflow, so there are a few goals that have guided our solution. First, we want the synthesis to so that the program updates can occur in real time. The kinds of updates we synthesize should be that the user can still understand their programming. We don't want to interrupt the workflow by asking the user questions. Did you want this? So in the rest of this talk, we'll explain how we implemented a live synchronization system that meets the. Let's start by looking at a simple example. A program that uses a loop to draw identical, evenly. Our design has several parameters. There's the box, the width and height of each box, and then the number of boxes. To actually draw the boxes 0, 1, and 2, feeding those index I will draw the ith box. Draws will have the same color, the same Y position, the same. The X position of each box will be calculated using this formula. We take the X position and then add the index times the separation. So sure enough, when we run this program, we get 3 evenly. Now, suppose the user comes in and from the X position of 110 over to a 115. We want to update the program to match. In particular, we want to change so that xi evaluates to 100, index is 2. What should we do? There's actually a lot of options for what we could do, and each of the different changes we could do in different ways. So, for example, we might change, okay, if the index is 2, then we'll use the value 155. Otherwise, this will translate the third box and leave the other 2 boxes. We might change x0, the x boxes together. We might instead change the separation. This will spread all the. In fact, we could actually change both x0 and sep. With all these options, which one should we take? Now remember, intuitive changes to the program. And one way to do that possible. Consequently, we decide not to do. For a similar reason, x0 and separation, because there's no clear way to say how much. That leaves us with either changing x0 or separation. We call these changes to only a single number in the program small updates. And because they are intuitive, they are the only kind of changes that our synthesizer will consider. Still, a question remains. Do we change x0 or do we change separation? Now, we could stop and or do you want to change separation? But one of our goals was not to interrupt the workflow. A heuristic to automatically choose and then change one of them. In this case, 0. Let's talk about how it makes. The first thing to notice is that this choice between 0 or separation is not just a problem we have with the first box, or we drag the second box, we still have to choose sep. So what do? Different program locations to different shapes. Each program location is assigned to some shape in the canvas. What that means is that the choice alternates between. The first box is assigned to change x0. The second box will change, and dragging the third box will change x0. And if we had more boxes, the box would change the separation, and the last box would change. We balance the number of times that each program location on the canvas. We talked about how we constrain the program synthesis search space to small updates, and we talked to decide exactly what to change. But we haven't talked about this expression here is the relevant expression. Box's x value came from that expression. We use instrumentation where output values are tagged with a trace of how each value was computed. With a assigned to 3 and b assigned to 5, normal evaluation of a plus b will. We tag each number with a trace that describes how the number was computed. So, tagged as coming from the program location A is tagged as coming from program location B, and then the resulting value 8 is tagged as coming from program location B. This gives us an execution each number was computed. For our box's example, this x position of 110 is tagged as coming from sep. When the user drags the third to solve, the right-hand side of the equation, the left-hand side of the equation is the new desired and adding the distance the mouse moved. Now we have heuristics assigned x0 to change when we drag the third box. x0 becomes a hole we solve for, and sep is replaced. Now we can solve this equation and get a new value for x0, which we put into the program and render the new output. In practice, we don't have before we solve and re-render, so we do it continuously as the user drags the mouse, which is real time. Traces are turned into equations that we give to a solver. Solver need to handle. So is tagged with a trace describing how that number was computed, and each trace is either a program literal in the AST, or it's a simple operation on traces, such as basic arithmetic or sign, pow, mod, etc. Thus, each trace is a of the equation we want to solve when we want a new number in the output. There are two things to notice about our traces. Track of any control flow information. So, for example, example, if B is instead computed based on a branch, resulting A plus B the result of 8 is only going to have of the branch that was taken. So even though we're throwing away this control flow, it still works out pretty well, at least for graphics. We wrote many examples. We wrote don't often branch, and even when they do, it's unusual during live synchronization. The second thing to notice about our traces is that whatever solver we use only needs to do high school math. Simple solver that can solve equations like these, the location being solved for only occurs once in the formula. If it occurs multiple times in the formula, our solver fails to compute. So this limits expressiveness. We found that for the examples we wrote, and we'll incorporate a more full-featured solver in the future. In all these parts of our solution, let's recap how they all fit together. We start by writing a program. Each number of the expression that produced that number. Manipulation from the user, we process each shape in the output one at a time to assign what program location will change if the shape is manipulated. We set the first box to change x0. The second box will change x0. Now, when the user drags the third box, which we solve for x0, we use this value to make a small update to the program. Immediately, we rerun the program and render the update and re-render continuously as the user drags the mouse. The user all of their mouse movements in real time. We implement a web-based system called Sketch and Sketch, consisting of about. Let's take a look at some examples. Sure enough, if we grab the third box, x0 changes. If we grab the changes. And if we grab the first box, x0 changes. If we hover over a box, we can see that this first box is going to change y0. Similarly, we can see some highlights in the code. The values highlighted in yellow, meaning that they will change when is highlighted in gray, meaning that it appeared in the output change. Constants are highlighted in green as they change. We talked about how the heuristics automatically choose what to change. Say that we're happy with the separation anymore. We can mark any adding an exclamation mark. Change this value during live. Now, dragging any box will modify x0 separation. Okay. We're not limited to change their width and their height. But what about changing the number of boxes? There's actually nothing on the canvas that we can drag right now. For a design parameter such as this, we allow the user to annotate the number with a range. This tells Sketch and Sketch to number. Is almost exactly the same, but now the Y position of each box is calculated based on a manipulation lets us change the wave amplitude. We could change before. for the Chicago Botanic Garden. The design symmetry is in. So if we move one control point of the Bezier curve, its mirror point will move as well. Here's our Sketch and Sketch logo. The position of the 3 polygons is actually calculated relative to a white rectangle that's behind the design. We can move the entire design and scale the entire design just like we could in a direct. However, unlike a traditional editor, the spacing between the polygons with a single parameter, which we can manipulate of the lambda symbol in our logo. Here's a Ferris wheel design. Imagine how difficult it would be in a traditional direct manipulation graphics editor. With Sketch and Sketch, it's easy. Other parameters as well. This tessellation pattern is based off the reflections and rotations of a simple. We can easily explore interesting variations of this design. Now, note that the lower frame rate for this example is not because of the solver, but instead is largely due to the greater number of objects on the screen, as well as unoptimized. For example, we are reparsing and rewriting frame. We might, in future work, change using ideas such as incremental evaluation. So far, synchronization allows us to easily modify design parameters. Synchronization enables users and library writers to. We already demonstrated the sliders built into Sketch design. We can easily make our own just by setting up a shape to use in the program. We can use this. In this example, 2 sliders attached to a rectangle corner. The slider. Now, shapes we don't want to design can be distinguished in the code with a helper hidden by our tool. Dimensional slider controls 2 values at once. Now, we could imagine a tool that provides these sorts of simple widgets out of the box, but no matter how many controls are built in, the user may still want to design custom interfaces. Live synchronization makes this possible. In this example, a 2D slider controls the number of tiles. Sliders control the number of colors, as well as the shape of each repeated element. And the program has been written on the side, toggle the visibility of the shape. When the design is complete, we can and then copy the resulting SVG code. We looked at some demos of some live synchronization interactions. If you'd like to play with, available online. We also have some demos on YouTube. If you just Google for Sketch and Sketch, including some previews of our more recent efforts. Speaking of this work is only a first step in combining programmatic way. There are a lot of avenues for further research. I want to mention 3. Tweaks to the live synchronization approach presented today. Knobs to turn in our current implementation, and a lot of in a first implementation. There's no reason to believe they're experiment with different heuristics, different solvers, and second, the approach presented to type up their initial program before any synchronization. We're exploring ways to allow the programmer to build direct manipulation. For this domain, to draw shapes directly on the canvas, as well as to specify between the shapes. These new additional interactions will complement. Finally, the motivation Combining programmatic and direct manipulation arises in many other web development and spreadsheets, presentations, and maybe even general purpose programming. Graphics to bring the benefits of this bidirectional. Now, our goal of the program and its output is closely related to the goal of many. The particular focus of our work is the backwards connection. Output back to the program that generated it. Program synthesis problem. The previous program can be constants inside the program are the holes to fill in. Manipulate something in the output, that direct manipulation example that tells us the constraint. Our live synchronization is most closely related to Wang et al. Their approach focused on modified a string in the output. They used execute to automatically update string literals. Automatic update was not available. They highlighted relevant locations intervention. Although we also our system handles numerics instead of strings. Manipulation workflow, we additionally implemented heuristics to allow automatic security. There are three broader categories of related work I'd like to briefly mention. The flow we achieve with live synchronization resembles constraint-oriented programming systems, such as Sketchpad and ThingLab. But in contrast to constraint-oriented programming, our approach starts with a more traditional, deterministic programming model, and we limit the use of constraints only to the synthesis. Our work also represents in bidirectional programming, some source data is kept a view of that data by a specific language. In contrast, in our approach, is kept in sync with changes to its output program written in a DSL, but by a fixed framework, such as Sketch and Sketch, which provides a synthesis in the other. Finally, the vision with programming by manipulation systems proposed by Brett Victor. These systems tend to start with a direct manipulation or programmatic features, often in a domain-specific. In contrast, our approach starts in the opposite direction. We start with a general-purpose programming language, direct manipulation features. We think our work may adapt to other domains, such as those mentioned earlier. So, in summary, with live synchronization, we write a program. We directly change the output in real time. Live synchronization is a fast, intuitive, and automatic domains. Thank you for listening.
Examples, the notion of an example could be, where the user moves several things and then you start learning just one object. Because it might be more natural to do a copy, and that would make sure that your heuristic does it.
Yes, it's definitely something we've thought about. And that is about working on in the future.
Hi, Andrew Myers from Cornell. I wonder if a graphical editor developed at DEC-Circ in the 90s. This is a and a drawing that you could manipulate. And
no, I haven't actually heard of that, so it'd be great to look into.
And I even wrote a little code on it. So,
thank you.
So I can imagine depending on how you.
Yes, when you drag something is, as you said, entirely dependent on. Since we're only changing constants in the program, if the constant doesn't change, what you system isn't going to find it. So you do have to think. You do have to think before you want to change. So how am I going to write the program so that what I want to, and that is a limitation, and it's something where we provide more tools to say restructure programs. Besides freezing constant saying don't change this. There's a single constant at a time.